Okay, so we're going to go over exam 1, and I can only do about 4 to 7 problems depending on how much time it is, and I will label them so that you know which videos you need to click on. So the first question says, how many of the following numbers have 4 significant figures? So down here I've put in the little map that I used in the other videos to decide how many significant figures something has and what is something that's significant and not significant. So for example, our leading zeros are not significant, meaning these zeros have no non-zero digit in front of them. Those are leading zeros, they're not significant. But remember that they are important. And then we have our in-between zeros, which are significant, and our trailing zeros that come after a non-zero digit that are significant. So looking at our 4 numbers up above on number 1, I'm going to underline any digits that are significant. So we know all non-zero digits are significant. So we have 3, 3, and 1. There's no decimal here. So this 0 is not significant. It's still important, but it's not significant. So this number only has 3. And we're looking for 4. All right, the next number, these are our leading zeros, so these are not significant. These are trailing zeros, and they are, and this is a non-zero digit. So we have 1, 2, 3, 4. Okay, we have scientific notation for the next number, and we have 1, 2, 3 non-zero digits and a trailing 0. So we have 4 significant figures. And remember, for this one, we do not count this in counting our significant figures. This just tells us how we want to move our decimal place. And then our last number, we have 1, 2, 3 non-zero digits, and then a trailing 0 that is not significant. So this one has 3. So when we're looking back, we want 4 significant figures, and we have 1, 2 numbers that have 4 significant figures. Question number 2, what is the answer with the correct number of significant figures for this problem? So this is one of our addition problems, and we're going to use the TI calculator for this, and I'll show you how we will type that in. Oops. So we always want to start with our parentheses. Then we can type in 4.392. Now I'm going to add another parenthesis plus. Parenthesis 102.40, parenthesis plus, parenthesis, and 2.51, parenthesis. So we get 109302. 109302. That's not our answer just yet because we need to go to the correct number of significant figures. So remember when we have addition and subtraction, and I wrote the rule down here. Oh, where did I write the rule? I think I erased it. For addition and subtraction, the significant figure rule is that we round to the least precise measurement, which means we round to the fewest decimal places in the problem. All right, so this one has, we go to the 3 decimal places, this one is 2 decimal places, and this one is 2. So we want to go to 2 decimal places. So remember that we go, what I like to do, how I showed you to do it, is I'm going to underline the 2 that we need, and I'm going to look at one more. That 2 doesn't do anything to our 0, so our final answer is 109.30 grams. And that would be D. Okay, perform the following calculation to the correct number of significant figures. So we have a subtraction now, and we are going to follow the same method where we're going to go over to our TI calculator. Oops, sorry guys, click, clear, clear. And we will type it in the same way we did our addition. So parentheses, 0.495 minus parentheses, 0.585. And we get, oops, I did the wrong problem. I'm so sorry. Okay, try this again. 1.08 parentheses minus 0.585. So with your TI calculator or any calculator you're using, you can do this simple one without parentheses. Show you what we get. We get the same number, but it's always good to just be in the practice of using parentheses for when you're doing multiplication with scientific notation or multiplication and division, but we'll do a couple of those problems. So our answer is 0.495. 0.495. And we need to go to the correct number of significant figures. And we know that we want to go with the fewest decimal places in the problem. So here we have 2 decimal places, and here we have 3. We want to go with the 2 decimal places. So we look at our 2 numbers that we want to keep, and we look at one more. Does that 5 change our 9? It does, and it kind of has a domino effect. So now we're going to get 0.50, which is 2 decimal places, and this is 2 decimal places. So our answer is C. All right, here I put a couple of visuals to help kind of remind you how we write scientific notation, and we'll do a quick refresher here. So the main number is called a coefficient, and it has to be less than 10. So you can't write 54.0 times 10 to the 7th. That's wrong, because 54 is greater than 10. So it has to be less than 10. This is your base and your power. The base is always 10, and the only thing that will change is our power. And it's going to change according to how many times we move our decimal place. So I'm going to rewrite our number, 0.00416. So I know I want to move my decimal to the right, because if I go to the left, I'm just going to get more zeros, and that number isn't between 1 and less than 10. So we're going to go to the right, and we're going to count 1, let's try that again, 2, 3. So if I move my decimal place 3 places, 4.16, and I'm moving it to the right, when we move our decimal place from a standard notation, which this is standard notation, and we go to the right, that gives us a negative exponent. But when we undo scientific notation and we go back to standard, this means that we would move our decimal place to the left. So it can get a little bit confusing. I would recommend memorizing one or the other. And here are 2 little notes you can look at that talk to you about scientific notation that are really handy. All right, so we have our number here, and we want to go to the correct number of significant figures. So we need to look at the significant figures in the original number. So we know that these, let's do these in red. These are not significant. They're important, but they're not significant because they're called leading zeros. So we only want to look at numbers that are significant. So that would be our non-zero digits. So we have 3 significant figures that we're working with. This number has 3 significant figures, so that's correct. Just for fun and just for practice, what if I added a 0 to this? How many significant figures does it have now? Now it has 4, and we would just add a 0, just like that. All right, So we have our answer, 4.16 times 10 to the negative 3. Always pay attention to your exponents there. So that would be D. All right. Now we have a multiplication problem. And when we do multiplication for significant figures, I'm just going to write a note here. So multiplication, division, the rule is we take the fewest sig figs in the problem. So first let's do our arithmetic, and then we will figure out our significant figures. All right, so we're going to do parentheses, and we have scientific notation. So this is a good time to refresh how we type in scientific notation. So I'm going to type in 4.16, and then instead of 10 to the, I'm going to do second EE. So let me redo that, because I'm going to show you. Instead of 4.16 and, where did it go? 10 to the, that's not the one we want to use. We want to use the EE. So 4.16 second EE, wherever it is on your calculator. That E stands for 10 times. And all you have to type in is your exponent, so which is -2. And remember, we need to do this negative down here, not the subtraction sign. Okay, and we're going to multiply by 1.2 second EE to the 4th. And we get 499.2. Come over here and write 499.2. But remember, this isn't our final answer because we need to go to the correct number of significant figures. Even though he doesn't specify that in the problem, you know that you have to go to the correct number of significant figures. So we want to look for the one that has the fewest. This guy has 1, 2, 3. We do not count these for significant figures. And this guy has 1, 2. So we're going to go to 2 significant figures. Let me get a different color. I'm going to underline the 2 we need, 1, 2. We're going to look at one more, and that changes our answer to 50. But that 50 and 499 are not correct, right? And if I write 500, that's only one significant figure. So he kind of gives you a hint in the answers. These are all in scientific notation. So if you've come across an answer where you round it up and you get 500 and you're like, wait a second, how do I get 2 significant figures out of 500? It only has one. You write it in scientific notation. So it would be, we want to go to 2 significant figures. Let me just write that down so we don't forget. Here's our decimal. We're going to move our decimal to the left, 1, 2. Okay, that gives me 5.0 times 10 to the 2nd power, +2 because we went to the left. So now we have 2 significant figures. We don't count these as significant figures. And so our answer is 5.0 times 10 to the 2. And that would be A. All right. In which state of matter do particles have the lowest compressibility? So compressibility is a vocabulary word that should be in the flashcards. It should be something that you are familiar with. Compressibility means how can you compress it down. So imagine taking like a squeezy ball and putting it in your hand, and you're compressing it, you're squishing it down. So it's asking which has the lowest. So what's something that can't be compressed? I put a picture here to kind of help remind us a little bit about our states of matter. So we have gas that has the highest compressibility, meaning that we can put this gas into a smaller container and compress it down, and that would be okay. Liquid is a fixed volume. We can compress it a little bit, but not nearly as much as gas. And then solids, I always like to think of solids as like a rock. If you have a rock, can you squish it in your hand and make it a smaller rock? You probably can't unless you're the Hulk. So our answer is going to be solid. The solid cannot be compressed or made smaller by putting it into a smaller container. If you take a rock and you put it in a container, and then you take that same rock and you put it into a smaller container, it's still the same size. Nothing has been compressed or changed.